A slab of insulating material of uniform thickness D, lying between plus and minus d over 2 along the x-axis, extends infinitely in the y and z directions as shown in the figure. The slab has uniform charge density ρ, and the electric field in the middle of the slab is 0. The initial point of confusion about this problem is that the figure itself is somewhat hard to read because of its distorted perspective. This direction, left and right, in fact extends infinitely, as well as up and down the slab extends infinitely. So describing it with this picture, which almost looks like a box, is quite misleading. Instead, it is much easier to think of this thing as a sheet with finite thickness, and the total thickness is d. Even allowing for the fact that the picture makes it look as though this is a finite box rather than an infinite thick sheet of material, the problem is further calculated by the fact that looking in a 3D perspective like this makes it actually very difficult to figure out and draw the appropriate Gaussian surface in order to get on with the problem and find the electric field. So what we're going to do is we're going to draw this infinite sheet of charge on edge, and so these two lines represent the boundaries of the material, and I didn't draw a top edge because it extends infinitely up and down the page. We will take the time to draw an x-axis on our diagram, as well as to recognize the coordinate system begins in the center of the slab at x equals 0, so that the slab itself can be symmetrically placed half d to both the left and to the right of x equals 0. This problem is yet another example of an object of infinite size. And when you have an object of infinite size, if you placed a finite total charge on it, q, then the charge density near you would be nearly 0 because that q would be spread out across infinity. For that reason, charged slabs like this are not given by their total amount of charge, but instead they are referenced directly by their density. So that when we do go to draw a Gaussian surface and get a charge inside, we're obviously going to be taking this density times some particular volume. For the first part of the problem, we would like to find the electric field outside the infinite slab. And so, for example, I'll draw this point with the green dot on the x-axis and say, what is the electric field there? As always, we imagine what other points may have the same electric field as the point in question. And so we draw a series of dots vertically and recognize that in addition to going up and down, these things go in and out of the page, and that as long as we keep the same distance of each one of these dots to our sheet of charge, we must be guaranteed that all of those dots have the same electric field. However, we also recognize that that surface is never going to close. We need to find a way to define an overall closed surface using that as part of it, and furthermore, we can't allow any of our surfaces to become infinitely large. And so for that reason, we are going to make this surface simply stop. It will stop when this end point has some area A. Well, our surface may be finite, but it's still not closed. In order to close it, we need to find more points at which we can learn the field. And an easy additional point that we can figure out would be a point that is symmetrically on the opposite side of the same sheet. Because since the electric field will always be away from these positive charges, the electric field running out at the sheet on the left must be the same as the electric field running out at the sheet on the right. We will once again cut this off so that it makes a finite area A, and in fact it is exactly symmetric with the one on the other side. Please keep in mind that although the artwork is imperfect, those two green surfaces are meant to be equal distances on each side of the center of the slab in order to assure that we have symmetry. Now finally, in order to close these surfaces, we're going to draw our last portion going straight through the slab itself. Nothing in this problem indicates that the electric field along those last two green dotted lines should be the same as the electric field on the first two green lines. Nothing at all assures that the electric field is of the same strength. However, we have a trick. We know that since this entire slab is made up of positive charge, imagine those charges are zombies in a wall, the electric field will point away from the slab at all locations, and therefore the sides that we have just drawn so as to complete the Gaussian surface don't contribute to the Gauss integral, because the E dotted with dA drops to 0, because the E is no longer perpendicular to those surfaces. We're now in a position to make short work of the Gauss law portion of this derivation. As in some of the other Gauss law problems, we notice that the surface we have generated has sharp edges and needs to be considered as multiple small pieces. We're going to define these multiple small pieces as two end plates. These are the ones of area A, so end plate 1 plus end plate 2. And we also have some number of sides. Moments ago, we completed an argument that the electric field does not poke through the sides of our Gaussian surface, and therefore these sides will contribute 0 to our final sum, meaning that all we'll have to do is calculate the flux through the two end plates. Each one of these two end plates gives a contribution of electric field times area. It's pointed outward at both sides. And then on the right-hand side, we will have Q in over epsilon naught. As always, we'll need to figure out what the area is. We've made an arbitrary sized area. It's A. We'll also need to figure out Q in. As stated before, since we've been given a charge density in the problem rho, we will be multiplying rho by some volume. If we go back to the figure, we can see what volume it is we should be multiplying by. The Gaussian surface has clipped a small piece of the infinite sheet whose size is denoted by the diagonal purple lines. In addition to the charge that is found inside our Gaussian surface, there is also empty space over here and over there. Thus, when we decide to multiply a charge density times a volume, it should not be the entire volume inside the Gaussian surface, because some of that volume is empty. It should only be the charge density times the amount of volume inside the Gaussian surface which is not empty. And that is a surface which has an area of A and a thickness of D. We are now in a position to plug all of this information back into our original Gauss law formula and thereby solve for the electric field. On the left-hand side of the equation, we still have EA plus EA, and on the right-hand side of the equation, Q in is rho area times thickness D divided by epsilon naught. As you'll remember, the area A was a crutch that we are using as a helper for solving the problem. The result cannot depend upon our choice of an arbitrary area used for the analysis. And indeed, you'll see that if you factor out the A from the left, it will cancel with the area on the right, leaving us with a simple expression for electric field that does not depend upon the area, and that expression is density times D divided by twice epsilon naught. For the next part of the problem, we'll again make a simplification of the original figure and draw this figure from the side. Once again, we have defined the origin of our x-coordinate such that the center point is in the middle of the slab itself. We have been asked to find the electric field at a point which is a distance x away from the middle of the slab. Let's begin by listing and indicating other points that we believe must have the same electric field as the place where we're doing the calculation. We could go infinitely up and down, we could go infinitely in and out on the slab, but in order to make the calculation finite, we will simply stop this process once we have mapped out a total area A, and recognize that the process of following this line is going to lead to an infinite open sheet. Neither of those two are good characteristics. So we need to find a trick by which we can close this surface and therefore solve the problem. In the text of the problem, a very interesting hint was given. And that interesting hint was that at x equals 0, the electric field must be 0. We can understand this by symmetry. There is equal positive charge to the left of you, and there's equal positive charge to the right of you. There are equal zombies to the left of you, and there are equal zombies to the right of you. Which way do you run? The answer is, you don't know, you stand still, you get eaten. So we are able to draw a surface through the center of the slab. And the key to this surface in the center of the slab is the following. It has zero electric field. Therefore, it is an end plate that will make no contribution to the final answer. Thus, using our former trick, closing top and bottom in parallel to the x-axis, we know that we will get no contribution along those last two lines because the electric field does not pierce them, it runs along them. We also know that we will get no contribution back here on end cap 1 because end cap 1 has zero electric field. Therefore, end cap 2 is going to make the entire contribution. Let's start again with Gauss' law written out in its full glory. We recognize that we have made a complicated shape with sharp edges, and so we're going to have to consider the various pieces of it separately. We're going to consider end cap 1, end cap 2, and the sides. Because the electric field does not pierce the sides, this term will drop away. Because the electric field is 0 at the midpoint, this term will drop away. And so our only contribution on the left-hand side of Gauss' law is the electric field at the place we're trying to find it times the area of that end of the Gaussian surface. And this will be equal to the charge inside our Gaussian surface divided by epsilon naught. We'll need to go back to the figure for a moment to figure out what is the charge inside. We can see that our Gaussian surface has selected a Qin that is equal to the volume inside the Gaussian surface and is indicated by the purple dashed lines. By inspection, we can see the volume of this. It has a surface area on both ends of A, and it has a thickness x, where x is the location where we're doing our calculation. Thus, we're able to go to our Gauss law, let the area be A, let Qin be a density times a volume, and the volume we use is the area of our arbitrary end plate, or end cap, times the position x. Plugging all of this information in, we have EA is equal to rho A x over epsilon naught, as we should expect, since the area A was a crutch that we used to solve the problem. The answer cannot depend upon that choice, and it drops away, meaning that the electric field is simply rho x over epsilon naught. I always like to end my Gauss law problems by making a sketch of the result, and in this case the sketch is going to attempt to tell us what is the electric field as a function of x, not a radius, because this is neither a sphere nor a cylinder, and there's going to be a logical tick mark along the x-axis. This tick mark is at x equals d over 2. Now in this case I've only drawn the electric field for positive x's, but by symmetry the same shape should apply reflected in the negative direction. Looking at the formula that applies for x less than d over 2, we see that it is a couple of numbers times x, so we expect a linear rise, following which the formula outside the infinite slab has no x dependence. It's simply a number, and that number is rho d over 2 epsilon naught. The final step in solving this problem is to place a tick mark along the y-axis, and we're going to place that tick mark at the value of rho d over 2 epsilon naught, because you'll notice we get the same answer regardless of whether we use the x less than d over 2 formula at this point or whether we use the x greater than d over 2 formula at this point. And that is the Gauss law solution of the infinite thick slab.